use it to find event profiles, so you can relate performance events, things like cache misses, to your code, find out where cache misses are coming from. It captures everything, drivers, kernel applications. What this means is if you're a driver writer or a kernel extension writer, you can use Shark to see the call stacks and find out where the time is being spent in your driver. And we're very low overhead because we're handling everything in the kernel. In addition, once you have your sampling session taken, we provide automated analysis. We attempt to annotate your source code and the disassembly of that source code to point out common problems and other things that you can do to optimize your code. There's a static analysis feature to find suboptimal code. So if you were in the earlier CHUD session, you know that there are some instructions that are on the G5 that you need to look for and watch out for, and this will help you find them. And we also provide optimization tips, as it says. There's a scriptable command line version. You can telnet in and sample things. And of course, you can save and review sessions and pass those around. So without further ado, the best way to see this, how to use the CHUD tools and Shark, is to have a demo. So for that, we're going to use the Noble Ape simulation. This is an open source program written by Tom Barbalet. And to help me demo, I'm going to bring up Sanjay Patel, also the Architecture and Performance Group. So first thing we'll do is we'll bring up Noble Ape. Okay, so here we are. We're simulating thinking apes on an island, a tropical island. And this map window is showing us an overview of the island, and the little red dots, each red dot is an ape. And we can focus in on one ape at a time. That's the ape with the red square around him there. And the brain window to the right here shows what his brain is, how the changes are occurring in his brain when he's walking around the island and thinking about things. So, every good performance study, of course, requires a metric. In our case, that's ape thoughts per second. This turns out to be the brain functionality is a performance critical in this application. So this is our metric. This is running on a PowerMac G5, 2 gigahertz dual processor machine, and we're seeing about 1,200 ape thoughts per second for each ape. So the first thing we'll do, we'll use Shark to see what's happening in the system while we run Noble Ape. So this is the main Shark window. By default, we go to the time profile, but there are other built-in profiles, of course, too, that take advantage of the performance counters. But for now, we'll just use the time profile. And we also have a global hotkey. You can put Shark doesn't have to be in the foreground to use it either. So let's sample five or so seconds and see what's happening. Okay, so here's the profile listing the important functions from most sampled to least sampled. And on the lower left here, we have the process pop-up, and this lists all the things that we sampled during this time period. Right, so at the top is Noble Ape, and we kind of expect that. We know that our simulation is CPU bound, but it's only 50% of the time. And you kind of wonder, well, okay, why is that? Well, if we go to the thread pop-up, we can see that, in fact, this application is single-threaded. And because it's single-threaded, we're not using half of our dual processor machine. So our first step in optimization was, hey, let's thread this thing we used the Carbon MP API and threaded Noble Ape. So let's see what the performance improvement was like. So remember, we had 1,200 thoughts per second before, and we're getting almost double that. So that's pretty good. But let's profile again and see what we can do with this code. All right. So now we can see that we're taking up a much greater portion of the time on the machine, and that's reassuring. We want to do that for our simulation. And, and we can see that we've spawned these threads now. We've got the main thread at 8%, and then the threads that are processing the apes in parallel, 40% apiece. So the next step we can do is we can double-click on any entry in this profile view, and it'll show us our source code colored with where the samples were taken. So what this tells you is what lines of source code the most time was spent on. Right? So if we look here, the scroll bar also gives us a way to jump quickly to the hotspot. So the hotspot is literally just this function, just this piece of the function, this for loop, inside of the cycle troop brain scalar function. So it turns out that this is about 94% of the time if we highlight this, right? So if we look, Shark gives us a hint on how to fix our code or how to make it better. So we click on this little exclamation point. It says, okay, this loop contains 8-bit integer. It's taking a lot of time. You're spending a lot of time in this loop. Maybe it would be worth the effort to vectorize this loop. So that was our next step. We went and we vectorized. So let's go back. Right. So we can run that. So remember 2400. Let's turn on vector. All right. So 10,000. That's nice. But we're still not done yet. Let's look again with Shark and see what else we could do. All right, so we see the vector function showing up there. We'll double click. And we're in the vector code. That's good. If you're a Shikari user, you probably know that if we had this disassembly view that was similar to this, and you can still get this back. This disassembly view is actually set right now to show G5 dispatch groups, and there's more detail on that in the full CHUD session. We'll go back to the source code for now. And if we look closely at the scroll bar, we can see that actually, even though we're spending a lot of time in the vector code that we optimized, now we're spending a relatively bigger portion of the time inside of the scalar code that we didn't optimize right before in the first step, that we didn't vectorize before. So our next step is, hey, maybe we should vectorize the rest of this since all these loops are fairly similar, and that's what Shark says to do. So let's go back to Noble Ape. So about 10,000, 9,500. Turn on vector optimized, and we're almost 15,000. So this is around 14 or so times the original performance. And what we're able to do is take advantage of this massive bandwidth we have available on the PowerMac G5 by using AltaVec. Okay, so could we have the slides again, please? Thank you, Sanjay. So, okay, we did that. Oh, wait, yeah. So just to summarize, we compared this against the PowerMac G4. So this is the scalar code running on the current PowerMac G4 top of the line against the PowerMac G5. And you can see that actually they're not all that far apart. In the scalar code, we have a longer pipe on the G5, a longer pipeline. And so we're not entirely scaling with this higher frequency. We're entirely bound in this CPU for this. So when we added the threading, we can see that we get a bigger jump than what the G4 got, right? Going from scalar to scalar threaded. Then vector, even bigger jump, and vector optimized, an even bigger difference, right? And the reason is that as we improve this code, we're more and more constrained by the memory bandwidth available in the system. Well, on the G5, we're simply not as constrained, right? We have a lot more memory bandwidth to play with here. So by vectorizing your code, you can, if we had just thrown this on the G5, we would see a very marginal improvement. But by putting the effort into vectorize, we're able to take advantage of a lot more of the system, a lot more of what it has to offer. So in addition to Shark, we have some other tools. Monster allows you to